So today we're going to look at Fibonacci number. Fibonacci is not a polygonal number or a figure eight number, okay? So that it doesn't follow a polygon, okay? It is different. So if you see these Fibonacci numbers, it begins with 0, then 1, 1, 2, 3, 5, 8, 13, 21, 34. Can you see a pattern here? Anybody knows what's the pattern here? First number, 0. Second number, 1. So 0 plus 1 equals to?
1.
1 plus 1 equals to 2.
2 plus 1 equals to 3, and so on.
Yes. So 1 plus 2 is equals to 3 and so forth. So that means when we have a number, we add the two numbers before it gives you that number. Okay. So what is the next number here? So 1 plus 2, 3. 2 plus 3, 5. 5 plus 8, 13. 13 plus 8 plus 13, 21. 13 plus 21, 34. What is the next number? 55. And one more number?
89.
89, correct. Okay.
89.
Okay. So say we have a number here, nth. Okay, this is the nth number here. Okay. So how do we find the nth number? If this is n, what is the number before n? If this is n,
233.
if this is nth, then if this is the nth number, then the number before nth will be n minus 1 number. The number before that will be n minus 2. Okay, so this is how it goes. So if we want to find the nth number, the nth term is equivalent to the n minus 1 term plus the n minus 2 term. Okay, this term here we use Tn. We can also use Fn because we are using Fibonacci numbers. So we can also use Fn is equals to Fn minus 1 plus Tn minus 1. Okay, Tn is nth term, or we can use Fn, nth term for Fibonacci numbers. We can use Pn, nth term for pentagonal numbers. Tn can also be used as the nth term for triangular numbers, or we can use Sn as the nth term for square numbers, or we can use everything as Tn. Okay?
Okay.
Okay. Okay, Fibonacci numbers. Okay, I'm going to show you another pattern here. Okay. Okay. If I write the number like this, 1, 1, 1. Okay. 1, 1 plus 1 is 2. Then another 1 here. Okay. Another 1 here. 1 plus 2 is 2 plus 1 is 3. And another 1 here. Okay. So what is the next line here? What do I write here? You see a pattern here? 4. Here?
6.
6,
4.
4 and
4
1. Okay, so you see at the end here, all the sides are all 1. So again, 1 here. Here will be
1, 5.
5. 6 plus 10. 6 plus 1, 5. 1. What is the next line?
1, 6,
1,
15, 20, 25, 20, 15, 15,
yeah, 15,
6, and then 1, 1.
6. And then end with the 1. Okay, very good. Thank you. Okay, so this is called Pascal's triangle. Okay, Pascal's triangle. So sometimes when you search for Fibonacci numbers, you come across this triangle. They give you this triangle, and they tell you this is Fibonacci numbers, but you are wondering why isn't your Fibonacci 0, 1, 1? What's the next number? 2, 3, 5, 8, 13, and so on. Your Fibonacci numbers like this, right? So sometimes they give you a picture like this, Pascal's triangle. So we can derive our Fibonacci numbers from here. How do we derive? Is like this, the diagonal 1, 1, 2. So this is 1, 1, 2. Okay? 3, 5, 8. This is 3, this is 5, 8, and so on. So these are the Fibonacci numbers. Fibonacci, sorry. Fibonacci numbers, Fibonacci sequence. Can you see that? Okay, 1, 1, 2, 3, 5, 8. 1, 1, 2, 3, 5, 8. Okay, so of course, because there's nothing up here, so it's a 0 up here. 0. Okay. Okay, so sometimes Fibonacci numbers, they are displayed like this, but the sequence is derived from the diagonals here. Okay, can understand so far? Yes?
Yes, madam.
Okay, good. Okay. 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 Fibonacci numbers can also be shown as a picture like this. Okay, this is a Fibonacci number. You see, this is 1, right? 1, 1, 2, 3, 5, 8, and so on. Okay, the length of the sides, okay, they show the Fibonacci numbers. Okay, the length of this square, the length of this side here, the dimension of this side here is 1. This square is 1. Both these squares have a dimension of 1. Okay, this square adjacent to it has a dimension of 2. Okay, this square adjacent to this has a dimension of 3. So all these numbers here are the dimensions of the square, panjang sisi. Okay, so 1, 1, 2, 3, 5, 8, 13. These are Fibonacci numbers. We can continue this picture. Okay, we can also draw a spiral here. Okay, it's like this. You see, from the 1 here. Let me try again. Okay, can you see the spiral there? A spiral is something like this. When you draw like this, this is called a spiral. Okay, or if it's like this, it's a spiral. Like this is a spiral, all the spirals. Okay, so we can draw a spiral here. This spiral is known as Fibonacci spiral, or it is also known as the golden spiral. Okay, because it follows the golden ratios. So it's called golden spiral. Okay. So this is how we can represent the Fibonacci numbers. Let's look at one more, okay? Let's see how we can draw that. Huh? Okay, say we want to draw the Fibonacci numbers shown earlier. Okay, say we want to draw it out, okay? The Fibonacci numbers. We know that our numbers is 1, 2, 3, 5, 8, 13, and so on, okay? So we start with a square with a dimension of 1, okay? So this square has a dimension of 1, correct? So we draw another square next to it with a dimension of 1. So this is 1 and this is 1. So the dimension of both these squares is 2. So we draw another square with a dimension of 2 on top of this. Okay, so this one dimension is 2. Okay, 2 here. Okay, so if this dimension is 2 and this is 1, so this whole thing is 3. So we can draw a square with the dimension of 3 here. Okay, so this is 3. So this whole thing now is 5, right? So let's draw a square with dimension of 5. 3, 4, 5. Okay, 1, 2, 3, 1, 2, 1, 2 is here. Okay, so this is 5, okay? Dimension of 5. With 5 here, this whole thing now is, how much is this whole thing? How much is that whole thing? What is this dimension now? 8, yeah, it is 8, yeah? So this is dimension is 8. Now what is this dimension?
13.
Yeah, 13, huh? Okay, so we can complete the square like this, okay? Each time we draw a rectangle, okay? Okay, so let's try and draw our spiral on top of this, okay? Once we've drawn this, we can draw our spiral. Okay, so which way the spiral going to go? It's going to go from 1, 2, 3, 5. So it has to go this way, okay? All right. Okay, like that. Okay. So where will our next dimension be? What's our next dimension after 13? How much is this whole thing? 13 plus 3 plus 5 is
21.
21, right? So our next square will be 21. I didn't measure, so it will be 21. And then our spiral will continue like that. So we can keep on adding the squares and we can draw bigger and bigger and we can draw the spiral. So in other words, we can represent these Fibonacci numbers this way, in a Fibonacci square and Fibonacci spiral. Okay? Okay? So this you can practice later. This is one of your tutorial questions. Okay. So the next thing, okay, about Fibonacci numbers. These Fibonacci numbers, they are very interesting. Mathematicians like to investigate Fibonacci numbers because, why? Because they have found a lot of interesting facts about Fibonacci numbers. And one of the most interesting facts about Fibonacci numbers is that it is seen in nature. Okay, a lot of plants, a lot of flowers display these Fibonacci numbers. Okay, let's have a look at some examples. Okay. Okay, let's look at these examples here. Okay, we have some flowers here. Okay, let's look at the first flower here, this orange flower here. Okay, let's count how many petals there are here. 1, 2, 3, 4, 5,
4,
6,
5,
7, 8.
6,
Okay, tell me what are Fibonacci numbers. 0, 1, 1, 2,
2, 3,
5,
5,
8, 13, 21,
13,
34,
34.
34,
34 after 34?
55,
55. Okay, and so on. Okay, so we have 8 petals on this flower, and we have 8 in the Fibonacci number. It is an element in the Fibonacci number. Okay, this purple or blue flower here. Okay, so how many petals? 1, 2, 3, 4, 5, and 5 is a number in the Fibonacci sequence. Okay, how about this flower? How many petals are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, there are 13 petals in this flower. Okay, it is also a number in the Fibonacci number. This is very interesting, right? If you pick up many flowers, you see that the number of petals is corresponds to elements in the Fibonacci sequence. Okay, how about this flower here? It's a sunflower, I think. How many petals are there here? I think you can count, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, anybody can tell me how many petals are there here? Okay, I've counted it and I think there is 34 petals. Okay, 34 petals. 34. So 34 is also a Fibonacci number. Okay, but let's look at this picture here. This is a picture of spirals. Spirals. If we count the spirals, okay, there's 1 spiral here, 2 spiral, 3, 4, and 5. 5 spirals here. 5 is the number in the Fibonacci sequence. Okay, how about this picture at the bottom here? This picture here, okay? If you look at the arrangement of the leaves here, they are arranged in a spiral pattern. Okay, so that we have 1 here, and then we have 2 leaves. Second round, second spirals 2, and then we have 3 here. 3, third round 3 leaves. Then we have 1, 2, 3, 4, 5, 5. So we're following that 1, 2, 3, 5. Okay, so the way the leaves are arranged in this plant follows the Fibonacci sequence. Okay, so if you look at this sunflower picture down here, okay, if you look at this sunflower picture down here, okay, you see there are a lot of spirals here. This is the seed head. You see there are a lot of spirals here. Okay, we can see many spirals. Of course, we're not going to count this today. Okay, then we can see that the spiral also goes the other way. Okay, we can see that it goes the other way also. So it is anti-clockwise and clockwise. Okay, the same thing with this pine cone here. You see there are a lot of spirals. If you look carefully, you can count the spirals, and it also goes the other way. Okay, and if you count these spirals, you will see that it is the same as the number, a number in the Fibonacci sequence. You see this shell down here, it also has spiral. 1, 2, 3, 4, 5. 5 spirals. Also equivalent to the Fibonacci number. Okay. Okay. So these are examples of Fibonacci in nature. Okay. Okay, that is why people like to investigate or do research on Fibonacci numbers, because they're such interesting numbers, and we see it all around us in nature. Okay. Now let's look at something else here. Okay. Okay, Fibonacci. First, came up with this problem in the year 1202. Okay, this is his original problem. He introduced this problem through this rabbit problem. Okay, he introduced Fibonacci numbers through this rabbit problem. Okay, so he said, suppose a newly born pair of rabbits, newly born, one male and one female, are put in the fields, and these rabbits are able to mate at the age of 1 month, so that at the end of the second month, a female can produce another pair of rabbits. Okay, if the conditions in the field are ideal. Ideal means that these rabbits, they never die, they have enough food and water, and at the end of every month, from the second month onwards, the female will produce one pair of new rabbits. Okay, so if this is the case, his question was, how many pairs of rabbits will there be at the end of 1 year? So can you figure that out first? How many pairs of rabbits will there be at the end of 1 year? Okay, so we see here the first pair of rabbits. These are the newborn. Okay, newborn rabbits. This is at the beginning of the month. We have one pair of rabbits. At the end of the month, we still have one pair of rabbits, right? This is end of the first month. We still have one pair of rabbits. When is this? When do we get a new pair of rabbit?
Third month.
Third month?
Second month.
Second month, beginning or end?
End.
Yeah, this should be the end of the second month, end of second month. Okay, so end of second month, we have the original pair of rabbits and they have reproduced. We have a new pair of rabbits here. Okay, so you calculate. So at the end of 1 year, how many pairs of rabbits will there be? Anybody? You just have to complete the sequence for 12 months, right? Okay, so you know that at the end of the first month, there is only one pair. At the end of the second month, how many pairs are there?
2.
2.
Okay, let's go for beginning of the month. Let's go for beginning of the month, okay? Let's see this. Okay, month. Let's go. Beginning of the month, okay? Okay, because the rabbits are put into the field when they are due. Beginning of second month, how many rabbits are there? Beginning of second month, that is when they are ready.
One pair.
Yes. So beginning of the third month, there is
2 pair.
2.
2 pairs. And then fourth month,
3 pair.
2 pairs. 3 pairs. Yes, 3 pairs already here. Okay. And then beginning of the fifth month will be
8. 5. 5.
5. 1, 2, 3, 4, 5.
5 pairs of rabbit, and then there will be 8,
8.
and then there will be 13,
13.
and then there
21.
will be 21,
1.
and then there will be
34.
34, and then 55, 89, and what more? After 89 is 144. So at the end of the first year, there will be 144 rabbits. Okay, so this is the original problem that Fibonacci investigated about how fast rabbits can breed. And he said this is the way rabbits breed. Okay, so we can calculate at the end of 2 years how many rabbits there will be if we follow this sequence. Okay, if we follow the sequence, we will know how many rabbits, how many pairs of rabbits there will be at the end of 2 years and 3 years and so on. Okay, so this is how we got introduced to the Fibonacci problem. This is the original rabbit problem. Okay. Okay, so I think that is about all for Fibonacci numbers. Okay, I want Fibonacci numbers. So we have looked at triangular numbers, square numbers, pentagonal numbers, and we've looked at Fibonacci numbers. By looking at these numbers, we've looked at number patterns. Okay, so let's try one problem solving question. Okay, this is the problem solving question that you are going to try. Okay, you are stacking logs. You know what are logs, right? Logs, kayu balak. Okay, you are stacking them. That means you are arranging them on one on top of the other. Okay, there is enough space for only 10 logs side by side. If you arrange the logs on the floor, say side by side, you only can put 10 logs. How many logs? Okay, you can try and solve it. Okay, you can draw. You can try drawing first. When you start drawing, you may understand what kind of numbers you're dealing with. So, anybody with an answer? Okay, you are stacking logs. There's enough space for only 10 logs. Okay, let's just draw this out first. Okay, so this is one log. 2, 3, 5, 6, 7 logs. So you have arranged 10 logs side by side, and there is no more space. Okay, no more space. Okay, you cannot arrange any more log after this. No more space here. Okay, so you are going to arrange the log. Stack means arrange one on top of another. That means you must arrange upwards now. So how many logs can you arrange? How many logs can you go right up? That's the question. So how many do you think? Okay, you tell me. This row, how many logs can you arrange? Right above these logs, how many can you arrange here?
10.
10?
Don't.
You haven't arranged logs before. Okay, if you arrange logs, you know that you have to arrange like this, right?
Oh,
You can't arrange on top of this, right? You arrange in the, okay, right? So 1, 2, 3,
4, 5,
4, 5, 6,
6, 7,
7,
8.
8, 9. Okay, what is the next row up here? How many logs?
1, 2, 3, 4, 5, 6, 7, 8.
Yes, 3, 4, 5. Okay, my drawing is not very good. Okay, 7, 8. Okay, so and so on until you reach the top. So how many logs can you fit in the stack?
Mm,
What is the shape of your log stack? What will be the shape of the stack be?
triangle.
Yeah, you know that it will be a triangle. So you have 10 here, 9, 8, 7, 6, 5, 4, 3, 2, 1.
1,
So how many,
40,
what's the dimension here? 10, right? What's the dimension this way? What's the dimension this way? You draw it out, draw it on a paper and see what's the dimension. By now you should already have an idea what number is this? What type of number is this? What type of sequence are we dealing with? I draw a nicer picture for you if I can. Okay, so I've drawn the stack here for you. So what is the dimension down here? Bottom here, how many logs are there at the bottom here?
10.
10. What is the dimension this way? 1, 2, 3, 4,
10.
5, 6,
10.
7, 8, 9, 10. What is the dimension this way?
10.
10 also, right? So what number is this? Okay, because you have learned triangular number is like this, right? Triangular number can be like this. It can also be like this, okay? Because this is also triangular number 10, 10, 10. The 10th term, right? 10, 10, 10. So this is also the 10th term. You can also draw like this. I think I remember I told you this, 10, 10, 10. Triangular number. So this is a triangular number, right? If the dot number of dots here are 10, 10, 10, what term is this? T10, right? So what is the formula for triangular numbers? Tn is equals to n
N plus N plus
1, is it?
yes,
Over 2, correct?
2,
So what is this? So this is 10
10,
plus 10 plus 1 is over 11 over 2. 10 times 11 divided by 2 is 55. So therefore, there are 55 logs. You can step up 55 logs. Okay, this is the kind of problem solving question that will come on the exam. Okay, so when you see a question like this, always draw. Okay, draw first. Because as soon as you draw, you will see the pattern. And if it looks like a triangle, then you know it has got something to do with triangular numbers. If it looks like a square, it has something to do with square numbers. Okay, if it looks like a pentagon, then it's something to do with pentagonal numbers. So if it looks like a triangle and you see all the sides and same, you know this is the 10th triangular term. Okay, so that's just an example lah. So the other examples you can go and search in the internet later. Okay, so with